Good morning, students. Good morning to all of you. Today we are going to discuss magnetic field due to circular current carrying loop at the center of loop. Okay, we have to find out the magnetic field due to this circular current carrying loop. Suppose this one, the circular current carrying loop. There is a loop, and inside the loop there is a current which is flowing. Suppose this one, the current here I. Okay, there is a current that is equal to I, and due to this current we have to find out the magnetic field at the center of the loop. Suppose this one, the center of the loop, and this one, suppose the radius of the loop. Suppose this one, the radius, that is equal to how much? A. Okay, we assume that the radius A for this loop. Okay, so we use here the Biot-Savart law to find out the magnetic field due to this circular current carrying loop. We cut an element here, we cut an element having a length dl, and due to this dl length there is a magnetic field at a center that is equal to dB, and due to this dB we have to integrate this dB and to find the magnetic field at a point P due to this whole dl length or whole circular current carrying loop. Okay, what is the Biot-Savart law? We know that here, suppose this one a wire, we know that this one the wire having current I, and we cut an element having a length dl, and due to this length dl we find the magnetic field at a point P having a distance r, and there is a theta which makes angle theta. The distance, the angle is the theta is the angle between the dl and r, and due to this element there is a magnetic field at a point P that is equal to dB equal to how much? Mu naught upon 4 pi I dl sin theta. Okay, sin theta upon r square. This is the magnitude of the dB at point P. Due to this concept, we use this concept to find the magnetic field due to the whole circular current carrying loop. Okay, let us see here. We cut an element having a dl, and this element having current direction in the direction of electric current. We also cut an element here dl, and the dl also having a direction in the direction of electric current, and we cut element here dl. This one the direction of element dl. This one the direction of element dl. Okay, this one the element dl. Okay, having a length dl. Suppose this one the length of whole wire L, so we cut element dl. Okay, and due to this dl we find a magnetic field here. Okay, let us see here the magnetic field here. What will the magnetic field? dB becomes how much? Mu naught upon 4 pi I dl sin theta. Sin theta, here the sin theta is the angle between the dl and r vector, or the it is the angle between the dl and r vector. R is the distance between the dl and point P. R is the distance between the dl and point P. Here the r becomes a. Here r becomes a because dl, r is the distance between dl and point P. Okay, this one point P. Suppose this one point P. The r is the distance between dl and point P, so r becomes a. I dl sin theta. Theta becomes how much? 90 degree. Okay, theta becomes here 90 degree because theta is the angle between the dl and a. Dl here, the direction of dl here, and this one the a. So dl and a having an angle 90 degree. Here the theta is the angle between dl and r. Dl and r. Dl and r. So the r becomes a. So dl and r having an angle 90 degree. So here we can use the sine 90 degree, and r square means a square. Okay. From here we find that the dB equal to mu naught upon 4 pi I dl sin 90 becomes how much? 1 dl I dl and divided by a square. Okay, and with the direction of this magnetic field we use the right hand palm rule or right hand thumb rule. We place our thumb in the direction of current, and your 4 curling fingers will give the direction of magnetic field. Here we see that the magnetic field be outwards. Okay, we write here outwards. Okay, and as you place your thumb here, we see that the magnetic field also outwards, and as you place your thumb in the direction of current here, also we see that the magnetic field in outwards, and when you place your thumb in the direction of electric current, we see that the thumb will also be outwards. Means due to the whole element, we know that the magnetic field be in outwards, so the direction is same, so we can integrate it because the direction is same for all elements, so we can integrate this elemental magnetic field for whole circle. This one for whole circle. Okay, this will give B and equal to mu naught upon 4 pi, it is constant, so come out, and I, the current which is flowing inside the wire, is also be constant, so it will be also come out, and the A square, that is the distance between the DL and A, also be constant, the radius of this circle, so it will also come out, and there is a DL will be inside the integration, this one for whole circle. And we know that as you integrate B equal to mu naught upon 4 pi I upon A square, and as you integrate the DL, we get the DL is the length of this element, DL, after integration we get the circumference of this circle, that is equal to 2 pi R is the radius, that is here A, the A square and A will be here cancel out, and the 2 pi also be cancel out here 2, and we get a magnetic field equal to mu naught upon 2 I upon A, and the direction of this magnetic field outwards. Okay, outwards. Okay, and as you reverse the direction of electric current inside the coil, the direction of magnetic field also be reversed. So we can write here note, as we reverse the direction of electric current in the circular wire, the direction of B also be reversed. Okay, reverse, and after reverse the magnetic field will be here inwards. As you reverse the direction of electric current, the magnetic field go inwards. Okay, I think you are able to follow me. Thank you very much.